Okay, so in this video, we want to look at examples of limits that are not giving us a direct case of 0 over 0 or infinity over infinity, but we'll show that we can rearrange the expression so that the case becomes of the type 0 over 0 or infinity over infinity, and then we can use L'Hopital's rule. So here's our first example. We are looking at the limit of x squared times 8 to the negative x as x goes to infinity. As always, look at the case that you have. As x goes to infinity, clearly x squared also goes to infinity. So this term here goes to positive infinity. Now here's the graph of 8 to the x, right? 8 to the 0 is 1. As x increases, 8 to the x becomes bigger and bigger. Think of it as 8 to the 1 is 8, 8 squared, 64, and so on. And when x is negative, if you think of it, 8 to the minus 1, that's 1 over 8. 8 to the minus 2, that's 1 over 64, and so forth. So as x goes to positive infinity, 8 to the x goes to positive infinity. But as the argument x goes to negative infinity, 8 to the x approaches 0. So here, if you think of it, as x goes to infinity, negative x goes to negative infinity. And if you take 8 to a power that goes to negative infinity, you see the exponential function base 8 actually approaches 0. So we have here an infinity times 0 case. And so as this stands, we cannot use L'Hopital's rule directly here. We can only use L'Hopital's rule directly if we have a 0 over 0 case or infinity over infinity case. The idea is, in the event of an infinity times 0 case, can we rearrange the expression to get a case that will allow us to use L'Hopital's rule? The answer is yes. Every time you have an infinity times 0 case, all you have to do is send one term on the denominator, either this term or this term. Here it's easier if we send this term on the denominator, because this will simply become x squared over, if you send this down, the negative exponent becomes a positive exponent. And now you get an infinity over, as x goes to infinity, a to the x also goes to infinity. So we have here an infinity over infinity case. And now we can use L'Hopital's rule. The limit stays the same, and we replace both top and bottom by their respective derivatives. X squared has a derivative of 2x. A to the x is the exponential function base 8. The derivative of this is the function itself, times the ln of the base. As always, we try and simplify. Here, no simplification is required. We look at the case that we're in. As x goes to infinity, 2x goes to infinity. A to the x goes to infinity, ln of 8 is a positive number, so we have infinity over infinity again. We can apply L'Hopital's rule one more time. The derivative of 2x is 2 over ln of 8 is a constant multiple of 8 to the x, so it will stay ln of 8, times the derivative of 8 to the x, which we know as before is 8 to the x ln of 8. And now look at your case. You could write this as ln of squared of 8 times 8 to the x, but don't bother. As x goes to infinity, 2 is always 2. What we have here is a multiple, a positive multiple of 8 to the x, but 8 to the x goes to infinity as x goes to infinity, so we have a 2 over infinity case. And so if you divide 2 by something which keeps getting bigger and bigger and bigger, the fraction will become smaller and smaller and smaller. So this will be shrinking to 0, and so the limit is 0. And there you have it. And you see, an infinity times 0 is not an obvious case, because which term will take over? Will the infinity be the bigger term, and way bigger than how 0 is small. So if the infinity term is really, really big, it may take over, and the limit could have been infinity. Here the 0 took over, the term was shrinking to 0 faster than the other term was blowing up, and so the end result was 0. You could have, and you'll see in examples on the problem sheet, sometimes with an infinity times 0 case, you'll get an answer of 1/2, -3/4, -7/8. When you have an infinity times 0 case, anything can happen. It's the same as a 0 over 0 case, infinity over infinity case. You never know what's going to happen in the end. So be careful about these kind of cases, but you see that without too much work, we were able to rearrange to a case that would allow us to use L'Hopital's rule. Let's do one more example of a 0 times infinity case. This is number 2. So we are going to let, in this case, x approach 0 from the right. And look at the product of x times the ln of x. As always, we'll try and look at what case we have. As x goes to 0, x goes to 0. We have a 0 times ln of x. What happens to ln of x as x approaches 0 from the positive side? Well, if you're not sure, sketch the graph of e to the x, keeping in mind that ln of x is simply the inverse of e to the x. Remember that e is roughly 2.71828, so it's just a standard exponential function where the base is bigger than 1. So the graphs of these functions all pretty much look the same. This is the value 1 when x is 0. Remember that the ln is just a logarithmic function base e, so by definition ln of x is the inverse function of e to the x. And to find the inverse, the graph of the inverse function of a given function, you simply have to look at the line y equals x and reflect the function about y equals x to get the graph of the inverse function. This point right here is the point x equals 0, y equals 1. So the point 0, 1 becomes the point 1, 0. So the ln of 1 will be equal to 0. And try and reflect this graph the best you can about this point. If you think of it here as x goes to negative infinity, y approaches 0 from the right, so you get the point, if you wish, negative infinity is 0, plus, which will become the point 0 plus negative infinity. So the curve will look something like this. And that's the y equal ln of x function. And now with the picture, you can see as x approaches 0 from the right, so x is approaching 0 from the positive side, we are asking what happens to ln of x. And you can see, let's take values of x that are approaching x equals 0, and look at the values on the ln of x function. Negative, a little bigger negative, a little bigger negative. And you can see as x approaches 0 from the right, the y values on the ln of x become larger and larger and larger, but always being negative. So as x approaches 0 from the right, ln of x approaches negative infinity. So we now have a 0 times negative infinity case. The sign doesn't matter. This is still a 0 times an infinity case. So as this stands, we cannot use L'Hopital's rule. The question is, how can we tweak the expression so as to allow us the use of L'Hopital's rule? Well, here we have two options. Which term do we send down? Do we send x down as a 1 over x? Or do we send ln of x down as a 1 over ln of x? The rule of thumb is, never send a logarithmic function to the denominator. Always leave it on top. So we have ln of x over, if you want to have a fraction here giving you an x on top, it is 1 over x. Right? If you divide ln of x by 1 over x, if you divide by a fraction, you multiply by the reciprocal. So if you do ln of x over 1 over x, that's just ln of x times the inverse of 1 over x, which is x. And so this equals this. And now with this form, let's look at the case that we are in. We've already said that ln of x approaches negative infinity as x approaches 0 from the right, over, as x goes to 0 from the positive side, we'll have here 1 over positive 0, which will give us positive infinity. The signs are not really important. What's important is that we have a negative infinity, an infinity over infinity case. The fact that the numerator is negative and the denominator is positive doesn't matter. We can now use L'Hopital's rule. So we have changed the 0 times infinity case to an infinity over infinity, and now let's use L'Hopital's rule. We're still letting x approach 0 from the positive side. The derivative of ln of x is 1 over x. When you find the derivative of 1 over x, don't use the quotient rule. Remember that simply 1 over x is x to the negative 1, and use the power rule, which will give you negative x to the negative 2. If you want as a fraction, that's just negative 1 over x squared, and that is the derivative of 1 over x. So we'll get negative 1 over x squared. As we've said before, if you divide by a fraction, you multiply by the reciprocal. So this limit will become the limit as x goes to infinity, the limit as x goes to 0 from the right, 1 over x, and if you divide by this fraction, you will multiply by the reciprocal, so times x squared over negative 1. We can simplify this, right? X squared over x is simply x over negative 1, so it's just negative x. And as x goes to 0 from the right, negative x also shrinks to 0. And so the limit is 0. So once again, we had an infinity times a 0 times infinity case, the expression being x times ln of x. We rearranged the expression so as to get an infinity over infinity case, and then we were able to use L'Hopital's rule. Simplifying the expression gave us a limit of 0. And the fact that two limits that we have considered so far were infinity times 0 case, and in each case we had an answer of 0, is simply dumb luck. You'll see on the problem sheet other examples of limits giving infinity times 0 times infinity case that will give you a lot of different answers. Sometimes it will be infinite, sometimes it will be 0, sometimes it will be 5 over 7, sometimes it will be negative root 5. Anything can happen with an infinity times 0 case. Let's look now at one other type of indeterminate case. This will be our third example and the last example of this video. So what if we looked at the limit as x approaches infinity of the cube root of x cubed plus 6x squared plus 4 minus x. Now if you look at this problem, it looks almost like a conjugation problem. We have a difference of two terms involving a root of some kind. But the method of conjugation only works, or at least works nicely, with a square root. What we have here is a cube root, so we have to use a different technique other than the method of conjugation. If we had a square root here, we could conjugate, and then would be able to find the limit in 2 or 3 steps. What's the case though? As x goes to infinity, this cubic polynomial goes to infinity, and the cube root of something which goes to infinity also goes to infinity. So we have infinity minus, well, as x goes to infinity, x goes to infinity. So we have an infinity minus infinity case. Once again, we have an indeterminate case because we know that something really big minus something really big could end up giving you anything. Maybe the first term is way bigger than the second, so we'll have a positive infinity as an answer. Maybe the second term is way bigger than the other, and we'll have a negative infinity, or maybe they're almost of the same size, and that could give us any real number. So we don't know what's happening here. And we cannot use conjugation because we have a cube root and not a square root. So it looks like we're at a loss. Because we can also not use L'Hopital's rule because we don't have a 0 over 0 case or an infinity over infinity case. Well, let's see if we can tweak this a little bit so that we then can use L'Hopital's rule. What I will do is factor from this cubic polynomial the power of 3. So it'll be x cubed times 1 plus 6 over x plus 4 over x cubed. If you want to check multiply across, you have x cubed over x is x squared, x cubed over x cubed is 1, and so this works, minus x. And now I'll use here properties of exponents. The root of a product is the product of the two individual square roots. So I'll have cube root of x cubed, that's just x, oops, times the cube root of the leftover term. 1 plus 6 over x plus 4 over x cubed minus x. And if you notice now, this is x times this minus x. Both the first and the second term are multiplied by x, so that's a common factor. Let's factor x from the expression. Well, the limit, as x goes to positive infinity, of x times the cube root of 1 plus 6 over x plus 4 over x cubed minus 1. And now let's look at what case we have here. As x goes to infinity, x goes to infinity. So this term goes to infinity. Times, as x goes to infinity, 6 over x and 4 over x cubed both go to 0. And we'll be left with a cube root of 1, which is 1, minus 1, which is 0. So we have an infinity times 0 case. So you see we went from an infinity minus infinity case to an infinity times 0 case. This is still not obvious, but we know how to turn a case like this to a fraction, so then we can use L'Hopital's rule. All we have to do is send one of the two terms on the denominator. Well, either we send x down or we send this down. Well, it's better to always send a simpler term on the bottom, so we'll send the times x as a division by 1 over x. And then you'll see that we will be able to use L'Hopital's rule. So thinking of differentiation, I'll write both of these as powers of x. 1 plus 6 x to the negative 1 plus 4 x to the negative 3. This will make the differentiation easier than using the quotient rule on both of these. Minus 1 over, as we have just said, 1 over x. And now if you think of the case that we are in, as x goes to infinity, both of these were going to 0. The cube root of 1 is 1. 1 minus 1 is 0. Over, and as x goes to infinity, 1 over x also goes to 0. So now we have a 0 over 0 case. And so now we can use L'Hopital's rule. So we apply L'Hopital's rule. The limit stays x approaching positive infinity. Let's differentiate. We have here the cube root of this function. The derivative of negative 1 is 0, so that's not a problem. The cube root is a power of 1/3, so we use the power rule, 1/3. 1 plus, and I'll write this as 6 over x plus 4 over x cubed. This will make the limit more obvious. Bring the 1/3 down. 1/3 minus 1, negative 2/3, times the derivative of the inside. The derivative of 1 is 0. The derivative of this will be negative 6x to the negative 2. So if you prefer, negative 6 over x squared. If you send the x to the minus 2 down, so negative 6 over x squared. This will give you negative 12x to the negative 4. Negative 12, x to the negative 4, you can send down as x to the positive 4. And that's a derivative of the inside. This completes the chain rule, the differentiation of our numerator over the derivative of 1 over x. But again, as we have done before, 1 over x is just x to the negative 1. The derivative of this is negative x to the negative 2. Send this, then you get negative 1 over x squared. All right, let's clean this up. If you divide by a fraction, you will multiply by the reciprocal, right? So we'll have here 1/3, 1 plus 6 over x plus 4 over x cubed to the negative 2/3 power times, you can factor from both of these if you want, say a negative 6. So negative 6 times, you'll be left with a 1 over x squared plus a 2 over x to the 4. And if you divide, as we have said, by negative 1 over x squared, you multiply by the reciprocal, which is negative x squared. And the idea here now is, well, cancel the negatives and multiply this term through by the x squared and see what happens. You'll see that by doing this, we will be able to evaluate the limit directly. So we have, oh, sorry, this was not 1/2, it was 1/3, my bad. So it's 1/3, 1 plus 6 over x plus 4 over x cubed to the power of negative 2/3 times, there's a 6 here, so times 6, times, and now we multiply across by x squared. So x squared over x squared is just 1, plus x squared over x to the 4 gives you an x to the 2 on the bottom, so you have 2 over x squared. And now, if you look at this, we can let x go to infinity. As x goes to infinity, 6 over x goes to 0, 4 over x cubed goes to 0. And so we have 1 to the power of negative 2/3, but 1 to any power is 1. So you see this nasty expression is just approaching 1. As x goes to infinity, so does x squared. So we'll have a 2 over infinity case. This goes to 0. And so this term will also approach 1. So in the end, what are we left with? 1/3 times 1 times 6 times 1. So it's just 6 over 3. And 6 over 3 is simply 2. And that's our final answer. So if you go back, this is rather a complicated problem. We had initially an infinity minus infinity case. We factored the x cubed, factored the x, then had an infinity times 0 case. We still can't use L'Hopital's rule, so we send the x as in 1 over x. Then we had a 0 over 0 case. We applied L'Hopital's rule, took the derivative of the numerator and denominator, simplify the expression, and finally letting x go to infinity gave us an answer of 2. So, as we knew from previous problems, a case of the type infinity minus infinity is not necessarily obvious. And you see in the end, both quantities were almost of the same size because they kind of canceled each other out, and the leftover is essentially So this is really a nice example of a limit requiring a fair bit of work before you can use L'Hopital's rule. You see, this was a bit of work, still not there yet, an extra bit of work, and then we can use L'Hopital's rule and obtain a limit of 2. In our next video, we'll consider another class of special types of limits that can still be used with L'Hopital's rule. There'll be just one new idea, and you'll see that the new idea will be to combine the natural logarithmic function as part of our solution.